So, have you ever stopped to wonder what is actually happening under the hood when an artificial intelligence learns? I mean, we hear buzzwords like machine learning, neural networks, and AI tossed around literally every single day. And we see the staggering results, right? Everything from generating photorealistic images out of thin air to translating languages in real time. But if you strip away all the hype, all the complex code, and the massive data centers, what is the fundamental mechanism that allows a machine to take a pile of raw data and actually learn how to make accurate predictions?
Well, spoiler alert, it's all driven by calculus. Specifically, the secret engine driving the most advanced algorithms we have today is vector calculus. And honestly, once you strip away the intimidation factor, the math behind it is incredibly elegant and, well, intuitively beautiful.
Welcome to this explainer. Today, we're diving into the mathematical compass, vector calculus, and optimization. We are going to unpack exactly how machines use mathematics to compute gradients, which then act like a compass, pointing algorithms straight to optimal solutions.
Here is our roadmap for today. 1. Finding the lowest point. 2. Meet the gradient. 3. The chain rule. 4. Navigating multidimensional tensors. And finally, 5. Gradient descent in action. Let's get right into it. Section 1. Finding the lowest point, or what we can call the landscape of machine learning.
Okay, so in machine learning, training an algorithm is basically just an exercise in optimization. Your ultimate goal is to minimize your model's error. Think of this as a rugged, physical landscape where the absolute lowest valley represents the lowest possible error. Our source material frames it perfectly, saying, imagine a surface with a ball starting at a particular location. When the ball is released, it will move downhill in the direction of steepest descent. But here's the catch. An algorithm is completely blind. It doesn't feel gravity like that ball does. So how on earth does it know which way is downhill?
That brings us to Section 2. Meet the gradient, your mathematical compass. To build this compass, we first need to get a handle on something called the partial derivative.
Now, in standard everyday calculus, a derivative just tells you the slope of a single line, simple enough. But in machine learning, we are dealing with multiple variables. Think of it as having multiple different directions you could possibly step. To find the gradient of a function with respect to just one specific variable, we vary that single variable while keeping all the others completely frozen or constant. Imagine you're standing on the side of a mountain in the pitch black. A partial derivative is basically like asking, if I take exactly one step north, how much does my elevation change? And then asking, okay, if I take exactly one step east, how much does my elevation change? You're just isolating one direction at a time.
But we don't just have one partial derivative, right? We have a massive collection of them, one for literally every single parameter in our model. When we gather all these partial derivatives together into a single row vector, we get what is known as the Jacobian. And this is huge. The Jacobian is the true mathematical generalization of the derivative for functions of several variables. This row vector is our gradient. It evaluates the slope in every possible direction and combines them to definitively tell the algorithm, hey, this specific combination of steps points directly uphill. And then, by simply flipping the sign to a negative, boom, we know exactly which way points directly downhill to our optimal solution.
Section 3. The chain rule. Linking variables. Let's see how this compass works when things get complicated.
In the real world, deep neural networks are complex. They're basically functions nested inside other functions, layer after layer. To find the gradient for a parameter buried way deep inside a model, we have to link these derivatives together. For vector-valued functions, the standard chain rule you might remember from math class elegantly transforms into a compact matrix multiplication. By multiplying the Jacobians of each layer together, we can pass that crucial gradient information backward through the entire model. And that right there is the absolute foundation of backpropagation. Section 4. Navigating multidimensional tensors. Scaling up, because yes, things do get bigger.
Modern machine learning handles massive datasets and millions of parameters, and it organizes them into multi-dimensional arrays called tensors. Now, don't let the word tensor intimidate you. A tensor is really just a manageable block of numbers. You can visualize it like a 3D grid, or maybe a cube made entirely of smaller cubes. Each little block simply holds a partial derivative. It's just a highly organized way to keep track of a massive amount of moving parts.
To put that into perspective, if we take the gradient of an M by N matrix with respect to a P by Q matrix, the result is a four-dimensional tensor.
Sure, the shape scales up, and yeah, the dimensions get a lot larger, but here's the beautiful part. The fundamental mathematical rules we just talked about, varying one variable while holding the others constant to find the slope, they apply exactly the same way here. We are literally just doing it thousands or even millions of times simultaneously.
And finally, Section 5, Gradient Descent in Action. Let's bring all this math together to see how it forces a model to reach that optimal solution.
So imagine our objective function is this red curve, and the dashed blue line sitting at the very bottom represents the global minimum, the lowest possible error we can achieve. Notice the arrows representing our negative gradients. The math ensures that the gradient points strictly orthogonal or perfectly perpendicular to the contour lines. This brilliant feature guarantees that our mathematical compass is always pointing toward the bottom of the bowl.
This entire elegant process is formalized into a first-order optimization algorithm called gradient descent. The steps laid out here are literally the heartbeat of machine learning. Step 1. Start at a random initial guess. Basically, just drop the ball onto the landscape. Step 2. Use vector calculus to compute the negative gradient. This is where you consult your mathematical compass. Step 3. Take a step downhill. Now keep in mind, the gradient only gives us the direction. The algorithm also has to dictate a step size to determine exactly how far we move in that direction. And finally, step 4, repeat the whole shebang. You calculate, you step. You calculate, you step. You do this until you eventually hit the minimum and your model is fully trained. But, you knew there was a but coming, right? There is a catch. Think back to that red curve we just pictured. It had a deep valley on the left, sure, but it also had a smaller, shallower dip on the right. What happens if our initial random guess drops our ball on the right side of the map? Well, the negative gradient will blindly lead us down into that smaller dip, what we call a local minimum, and the algorithm will just stop, happily thinking it has solved the problem, while completely missing the true global solution on the other side of the hill. It's a stark warning straight from our source material about the hidden dangers of the mathematical landscape. So I'm going to leave you with this provocative thought. If our compass only ever knows how to point downhill, how on earth do we teach a machine to climb out of a local valley to find the true global peak of its potential? That right there is the next great puzzle of optimization.